Okay. Yeah. Okay. Let me introduce our speaker today, Jonguk Yang, from University of Zurich. And the title of the talk is a priori bounds for unimodal diffeomorphisms in dimension 2.
Thank you very much. So thank you very much for the invitation. It's an honor to be here. I guess, okay, so hopefully the camera works better during the talk, so you guys can see those of you who are participating with Zoom. Let me start with the 1D case, with some more familiar setting. So in 1D, a map is, you define a unimodal map, and probably most of you know what a one-dimensional unimodal map is. So F, which maps from an interval into itself, which is C2, is unimodal. Model if it has a unique critical point, and let's say for simplicity that it's a quadratic. C naught inside of I, and for sake of simplicity, we'll do a quadratic type, although it can be other. So if I can just draw a little picture. Representing how it acts on the interval, acts on the space, then in a unimodal, if it does the following, it has a unique critical point, I back into itself, and the way it will map is it will take this interval and then it will fold it, right, at this point, at C0, and then it will map it to the critical value, which I'll call C1. So what we'll do is we'll take this interval, and we'll take the left half, and then we'll fold it into two, and we'll take this interval, and we'll fold it into something. So this is the action. Okay, so this is a 1D model. And this critical point plays a very important role in shaping the dynamics of unimodal map in all senses of the word. So it shapes it sort of combinatorial, it comes. And this critical point is recurrent, so you can keep iterating the critical value, it returns back to itself to keep going through this folding. And the strongest kind of recurrence you can have is when it's infinitely normalized. So let me define what that means. You say that F, well, first let me define what it means for F to be once renormalizable and actually normalized. F is renormalizable. If it has, okay, so there are different ways to define it, I guess, but let me just define it as if there exists a periodic sum, J. So that maps I into itself. You need sub-similarity at a smaller scale. So if there's some smaller subinterval, which we'll call J. And when you iterate on J, it'll map in the phase space. And then after R period, where R is some number bigger than 1, it returns back into the small range. Start iterating on J. it'll move, I don't know, here. And if F is infinitely normalizable, once F is infinitely renormalizable, then there should exist not just one periodic subinterval, but an infinite nest of periodic subintervals, smaller and smaller periodic subintervals with larger and larger periods. Right? So if it's infinitely normalizable, then the periodic subinterval itself has another periodic subinterval, and so on. There's a smaller interval. So let me call the first periodic subinterval J1, and then there should be a smaller periodic subinterval, let's call it J2, which is periodic with periods, some multiple of the period of J1, and so on and so forth. We have this infinite nest of cycles of periodic intervals, and when you take the intersection, you get some kind of cantilines, which we will refer to as the odometer. Odometer. Let me make some notations. So it's infinitely normalizable if then there exists R and periodic subintervals, J and which are nested, and we have the odometer, which I'll denote by lambda, and it's defined as the intersection of the union of the images of these periodic subintervals. Right? So it's the intersection of the union of the images of these. To make the point that a priori we have some candidates. In order for it to be a candidate set, it needs to be totally distinct. Each connected component needs to be a singleton. And to actually know that, you need to know something about the geometry of this dynamics. Right? Because what could happen is that when you take some infinite nest of these intervals, they might not shrink to point. The diameter might not go to zero. Right? So in order to guarantee that it's actually a candidate set, you need some kind of geometric control, which come from something called a priori bounds. So let me just loosely define a priori bounds at this point as some kind of uniform control on the geometry of this map, which holds that arbitrarily deep space. That will be kind of an intuitive philosophical definition of what a priori bounds is. And in this setting of one-dimensional unimodal maps, we do have a priori bounds. It's due to Dennis Sullivan, I think in the 80s. And as a consequence, we know that indeed this tangent-like set is actually the tangent set that is totally disconnected. And moreover, we can say that it's actually the closure of the so this is a story for a lot of you in one-dimensional case. And what I'm going to talk about today is generalization of the story to a two-dimensional set. And it's joint work with these three co-authors, Sullivan, Ika, and Enrique. So our goal was to take the renormalization theory of 1D unimodal maps and generalize it to what we're calling 2D unimodal maps. And actually, it will take maybe probably half the talk just for me to define what it means for a 2D map to be unimodal. But that's for a good reason, because a substantial part of our project was to identify what plays the role of a critical point in this higher dimensional set. Okay, so that will take us a fair bit of work just to get to that point. And then afterward, goal, generalize renormalization. To 2D unimodal. Let me put this in quotes, because right now there's no meaning to this description. And then, so once I define what this even means, then I will state the main theorem, which is upper bounds for these maps. So you know, all maps, and let's say it's infinitely normalizable. So we have some kind of small scale structure for these maps, and we will say prior to the main result. You know, is upper bounds, for these maps. And then, yeah, in the remaining time, I'll not have time to go through the proof in much detail, but I'll try to emphasize the difference between the one-dimensional case proof and the one-dimensional case and proving the two-dimensional case. What the main challenge is in going from 1D to 2D. Difference in 1D proof versus 2D. This is kind of the outline of what today's talk is going to be. Any questions? Okay, all right, so now I'll just okay, so let's set up our system. So now this was 1D, now let's talk about it. And in 2D, our map will be, well, it will map a subset of the two-dimensional space, and the analog of an interval in 2D is going to be a Jordan disk. So let's omega be a Jordan domain. So just draw some this looking like this, and F maps this domain into itself. F maps omega compactly into itself as a C2 so what this means, means is that the Jacobian of F is strictly less than 1 at all points. So it's strictly area contractible at infinitesimal level. Infinitesimal. So dissipative means that the supremum of the Jacobian of F is strictly for all points. So F takes this Jordan domain and it maps strictly inside. Right, so that's the setting. And then before I define what it means for such a map to be in a model, let me first define what it means to be renormalizable, because it's much easier. So the definition, F is renormalizable if, well, it'll be really analogous to the 1D definition. So it's renormalizable if there exists a R periodic Jordan subdomain. Let me call it D inside omega, such that R to the period of this domain maps compactly. So the picture looks something like this. You have some subdomain D, and then when you map it by F, it will go around the phase space, and then after R iterates, it will map it compactly. So that should be, I think, a pretty reasonable definition of what it means for F to be renormalizable. And okay, and
is it quadratic like?
So I mean, so far we haven't talked about the critical points, so we don't. Yeah, right now we can't really specify what it means for such a map.
Smaller domain A1 is the join.
Oh no, I just yeah.
About critical points because
yeah.
I can without more.
Yes, that's right. So these are all, yeah, these are all.
I mean, can touch boundaries.
I suppose they could touch at the boundary, but it's yeah, it doesn't. It's not really that. Okay, it's good. All right. so that's what it means for these maps to be renormalizable. And uh,
Homomorphic matters. They touch alpha points. Here maybe it doesn't. Yeah. It's hard to see.
So we'll make the following assumptions before defining what it means to bounds being the model. Yeah, I think in general, somehow in 1D, this kind of whether they can touch the boundary or not, it's how should I say? In 1D, everything is so precise. Whereas in 2D, I think yeah, it's very rare that you get two domains that kind of just touch the boundary. And yeah, so usually if you can get this joint that's up to the boundary, you can just get this joint. Because everything is kind of much more flexible and much less rigid. But okay, so let's make two of them. Assumption one. Is that F is infinite in 1. F is infinite in 1. And let me draw the next picture because we'll come back to this picture time and time again. So we again have this and shape. F. F maps this Jordan this logical this. Happens the return, the period number the zero count. This is D1, and then inside D1 there'll be another periodic subdomain. That's D2, and then it will map around, and back, around, and then it will map back. It's again, and then again we have this infinite nest. So if you take the intersection of all of them, you will get this tangent-like set, which we again call the odometer or the renormalization list. So infinite renormalizable. So there exists Rn periodic Jordan subdomains, Dn, which is compactly contained in Dn. So, and we define the odometer to be the intersection of the union of the cycles of these domains. And we map it by their period, and we take the intersection overall. So once again, we run into this problem. The limit set, what kind of set is it? Is it a tensor set or not? And well, a priori, we don't know. And I assume, I suspect that at least for just an arbitrary diffeomorphism to diffeomorphism, you'll have cases where it's not a tensor. But it will follow as a corollary of the upright bounds that we will state that for unimodal maps, if F is unimodal, whatever that means, then indeed this intersection will be totally disconnected. And not only that, it will be the same as 1D, it will be the closure of the critical. And this will be equal to closure. This is a little preview of where we're going. Questions of this question? Okay. All right. So that's assumption one. I'm going to say assumption two, but before I do that, let's go back to the screen for a little bit. About how we're going to sort of approach studying the geometry of this object. And And we'll start with the following observation. Which is that so you take this limit set, this odometer, and it's an invariant set. So you can assign some kind of Leopold exponent to this set. And the observation is that the Leopold, it has two Leopold exponents because it's 2D, and the Leopold exponents are going to be 0 and something negative. So Leopold exponents. F, suffix lambda, are 0 and something negative. Let's call it log lambda. Let's call lambda less than. So what does this mean? So it means that for a typical point in the odometer, let me take a typical point. Let's say P is a typical point. Then it has two directions, two distinct directions. Let me call it ESP, for stable direction at P, and ECP for the center direction at P, and the Leopold exponent being 0. Log lambda iterates of the derivative of that along the stable direction. Then as you go forward, on average, you experience exponential contraction by lambda. So as you go forward, when you iterate f and you look at the derivative and the growth rate of that derivative along the stable direction, then on average, it'll be like lambda. It'll be exponential. Yes.
So this information is a theorem.
It actually is.
And then it's probably booked exactly in the same way as it's done, and which might be otherwise it's very non-likely.
Not quite. So actually, okay, so I'm cheating because you actually need observation 2 or assumption 2 in order to prove this. It's actually, I'm trying to kind of pass it off as kind of a self-evident kind of result, but to actually prove rigorously,
Not 11 shows some improvement in holomorphic case.
Yeah, actually, I was going to mention.
Always non-negative.
Yeah,
it's almost zero. We need to assume there is a sequence of stuff like that.
Yeah. Okay, but let me go forward and I'll comment on it when I make assumptions. So, well, actually, what you need to prove is that what you have here is actually uniquely defined. Because when you talk about the Leopold exponent, you have to talk about it with respect to the invariant metric. It's not necessarily uniquely erotic if it's not here. If it's totally expected, then yeah. Well, actually, no, you don't need. You just so to prove unique perpetuity, you just need to show that almost every component is. Yeah. So this, okay, but let's just pretend that we don't have these subtle issues, and that we have these Leopold exponents, one of which is negative. So the negative corresponds to the stable direction. It says that as you go forward, there's exponential contraction on average, and as you go backwards, well, it'll be the opposite of exponential contraction, which will be exponential expansion. So as you go backward, things expand, and along the stable direction for the typical point, on average, it will expand like minus. And the center direction is the neutral direction. So that corresponds to the exponent 0. It says that as you go forward or backwards, on average, it'll be something sub-exponential, right? It'll be something neutral. It'll be like 1. 1 to 2. Okay. And once you have these, oh, and by the way, it's just at an intuitive level, it's kind of either convince yourself that these are the right equation of exponents for the set, or well, it's easy to convince yourself that there should be a neutral direction, because on the odometer, there's no hyperbolic expansion. So towards the odometer, then it shouldn't experience an exponential expansion. Dissipative, if it's neutral in one direction, then it should be happening. So that's how you get the negative. It's kind of an intuitive argument for why this is right. And once you have the stable direction and the center direction, then you can associate with it invariant manner. Okay, so we can show using a function too. Say it again. That at least almost every component is a single.
No, I'm asking how important is that to get a zero?
Oh, to get to zero, it's very important because the fact that you have zero is a consequence of unimodal.
Which we don't have. We try to prove this.
Yeah, so it's something that you can prove with the assumption about states. In just 1 second, but let me just define. Well, let me introduce kind of the main characters in this talk, which are the invariant manifold, the stable manifold, and the central. So if you have a stable direction, then not only is it some kind of infinitesimal statements about the dynamics at P, but you actually have a smooth one-dimensional curve, which we call WS at P. So this is a stable manifold at P. And along this curve, you will have asymptotic exponential and it's invariant. And along the center direction, you have a center manifold. Look at this picture, is pretty messy. So along the neutral direction, you also have this invariant one-dimensional manifold, which is, on which the map acts like a neutral map. There's sub-exponential contraction and extension along this. And it seems to me that when you're trying to figure out the geometry of higher dimensional dynamic systems, it really boils down to what do these invariant manifolds do? That's really the importance. And I think for me, what helped me understand just what they mean and why they're so important, it helped me to try and relate them to what they would be for one-dimensional systems. So let's look at the 1D case. Let's go back to the 1D case for 1D. So we care so much about stable and center manifolds for 2D. Well, then they should have some meaning because we're generalizing the 1D theory. They should have some meaning in the 1D case as well. So if you have a one-dimensional dynamical system, and this could be R1 or it could be C1 as well, or C1. If it's a one-dimensional dynamical system. Then what are the stable and center manifolds in this one-dimensional setting? Well, if you have a point, P, then the stable manifold will be, well, okay, so you can kind of represent it as an artificial vertical line that goes through that, right? And the way F maps this vertical line is just it collapses that line completely to the image. So that will be the stable manifold. Actually, that's not exactly true. It's not the stable manifold, it's the local stable manifold. This vertical line. If you want the full stable manifold, then you should take all pre-images of P under F. So F inverse of P, F P minus 2, and so on. So you take all pre-images of P under F, and you should draw a vertical line through all of them. And that would be the global stable manifold. That's what it corresponds to. And the center manifold is more subtle. And a lot of people don't like center manifolds because I said they're invariant manifolds, but they're not actually globally invariant, they're just locally invariant. So what that means is, if you have P, let's say, and you have the image of P, and you have the center of manifolds here at P, and you have the center manifold here, C of P, then it's not actually globally invariant in that you can't take the whole thing and map it forward and expect it to be invariant. What you need to do actually is to take a smaller subset, a subcurve containing P, and if you iterate that forward, then that will be. So you have this kind of weaker than global, you actually have a more so local invariance. And the longer iterate that you take, so if you take a longer iterate at N of P, then the smaller the subinterval that you have to take to guarantee invariance. Okay, so you have this. You're guaranteed invariance as long as you take smaller parts of this curve. So that's how the center manifold relates to the dynamics of F. And for 1D system, you can think of the center manifold of a point as, well, it depends on how many iterates you want to take at P. So if you take n iterates of P, the center manifold which will be preserved under this dynamics is the largest complement among P. It's called IP. Okay, so it's the largest interval on which F maps diffeomorphism. So that you can think of as the central manifold corresponding to the distribution. Okay, so this is the kind of meaning that the stable manifolds have, which can be transferred over to the 2D case. And indeed, if you think of F as not just X goes to F of X, but if you think of it as a degenerate 2D map, so if you think of it as XY goes to, let's say, F of X 0, that's a kind of a degenerate mapping of the 2D plane. Then if you were to perturb this to some 2D map, let's say F, XY. So if you take a degenerate 1D map and then you perturb it to a 2D map, then these manifolds will actually deform into the proper invariant manifolds in the two-dimensional space. Okay. Questions about this so far? Okay, so finally, let me state assumption 2.
Oh, sorry. It's a stupid point.
Yeah.
So if these are points, this is an orbit in campus, right?
Yeah.
This P. There are no comparables from those points because the numbers don't come out.
So I mean, it'll be a cantor set embedded in R, right? And the map will be applied on R, and the cantor set will use an invariant subset.
But then I mean, there is a critical point.
Yeah, the contour depends on the critical point. Then there'll be some neighborhood which will avoid the critical points, but that the size of the neighborhood will depend on how many edges.
But the moment you get the critical orbit and goes.
Well, actually, so as long as P is not an exact pre-image of a critical point, you can always find some non-zero neighborhood, right? No matter how big n is. It's not for n infinity, but for any finite n, you can always avoid the critical point. Right? Okay, assumption 2. Assumption 2 is that F is properly dissipative. So what does this mean? It means that, okay, it means that, so you have F mapping omega into itself again. And we talk about how for a typical point, you have the stable local stable manifolds going through this one. Yeah. It's properly dissipative if for almost all of these stable manifolds, the stable manifolds are global in the sense that it separates omega. So we say that these manifolds are proper. I.e., almost every stable manifold is proper. And so if you take almost every stable manifold, it will separate the domain into two pieces. So once you have proper dissipation, then you show that, yeah, you can't show right away without that for almost every.
I still don't understand. Will W is global or local?
Oh, so I mean, so local. So if you take a local, well, I mean, how do you define local? So let's say you take a global stable manifold. Yeah. Sorry, which?
Omega.
Omega. Yeah, omega is the original domain. Yeah. So you look at the domain of that, and if you take almost any stable manifold, it should split it in at least two pieces.
Okay, but it depends on time. Shorter is finest.
Oh, no. So the stable manifold is defined.
I mean, stable.
The stable. Yeah, the stable. Yeah, exactly. Okay. Proper. So we say a curve is proper in the domain if it separates the domain. Or okay, so it's proper in that, or it's separates.
Can be any number.
Yeah, it can be any number, but at least that's feature. And this gives our map. So this is why this assumption is so important, that it gives it a kind of quasi one-dimensional structure. Right? Because a very important feature of one-dimensional dynamics is that if you take a point, you can partition the dynamic, the phase space using the orbital point. Using the orbital points of the map. Right? So if you take a point, it's separated into two pieces. Right? So that's a very, very important feature of one dynamic, which you obviously don't immediately have in 2D. If you puncture a domain, a two-dimensional domain, it's not going to be separate, right? Okay, so that's why I kind of waited to introduce it until after this. So let's say for the invariant measure for almost every so the original definition is for any ergodic measure reported on a subset of omega, almost every stable manifold with respect to that measure should happen. You used to focus on delta. Supported on. No, no, you mean lambda?
No.
Yeah, so that's what we're interested in. But we can define proper dissipation without referring to renormalization, right? So yeah, so just for any ergodic measure. Something. Okay, so it's not usually okay, so it depends on what you mean by easily verified, but there is an important class of maps for which it's true, and it's renorm maps with Jacobian less than 1 point. Then it's true. So I'll talk about that.
So it looks like lamination.
Yeah, it looks like. And you can kind of try to use points to partition out a linear order, at least not right away, right? Because you could try to say that if you have a configuration like this, well, then you can say that this comes first, this comes second, this comes third, etc. Yeah, exactly. But then you could have a picture like this, and that ruins your day, right? And in general, you will not in general, you will have a picture like this. And so it doesn't immediately give you a one-dimensional order. Okay, so those are the two assumptions, and now I can try to transition into defining unimodality. But one more thing before I do this, and that's actually very important. So if we go back to this picture and we try to figure out the geometry of the stable and central manifold, the standard kind of approach to try to understand what that does, what that gives him, what the geometry of these manifolds look like. So it tells you something like for sets of large measure, for stable manifolds of large measure, there's some uniform lower bound on how bad the geometry can be set. It gives you these kind of statistical properties, but it's not quite good enough for us because at least for one-dimensional maps, the most important orbit is the critical orbit, which is a highly atypical orbit, right? And if you use measurable constant theory, you only see things up to measure 1. You don't even see what the critical point is there, right? So we needed to adapt this standard constant theory into what I'm calling quantitative constant theory. And here, this will tell you about the invariant manifolds of any point in your invariance, not just the full measure points. You don't have to throw out sets of measure 0. But the issue is that you have to work with very explicit inequalities for the quantity. So you have to do everything explicit. But you can get information about everything. So this is the most technical part of this talk, so just bear with me. But it's quite advanced. So how does this quantitative dissipative work? First, we have to fix two constants. Let's fix epsilon, so it's very, very small. Not quite, because even if you have a uniquely organic system, the oscillative theorem still tells you. Oh,
why it is better.
That's interesting. Actually, well, yeah. The hope. I think. I mean, the way I formulated it should be true even for non-uniquely organic systems. But maybe why it was so useful for us is because of. But okay, let's pick two constants. One really, really small, and one which is bigger than 1. L, which is bigger than 1. So quantitative dissipative theory, it tries to tell you what a nice behavior is of the model. Okay, so a nice a point behaving nicely, we call it a regular point. So we say P inside lambda is, and we're going to define 3 different types of regularity. So the first regularity is what I'll call forward regularity. So P in this pedometer is, let's say, forward L epsilon regular. If the following is true, so it has a stable direction, such that if you stop. Okay, should I pause or can I keep going? Okay. Then we say that it is L epsilon forward. Okay. And I define 2 other regularities. So there's backward regular, L epsilon regular, and this is going to look similar. So there should be a center direction at P, such that if you measure the growth rate restricted to, and this is for all n bigger or equal to when you go forward. So this is why it's forward regularity, you're only looking at forward, right? This will be backward regularity, so we're looking at the backward index. So we take the backward orbit, restricted to the center direction, and ideally it would just be 1 to the n, right? But you're not going to get that. So for forward regularity, you allow lambda to the minus epsilon room for error will allow the same, but because when you go backwards, things tend to expand, but if it's neutral, it shouldn't expand. But if this upper bound as kind of max, backwards things tend to sin L epsilon regular if, well, first of all, it's forward regular and backward regular, if 1 and 2. But it's not just 1 and 2. You also have to have the following condition. And if you measure the angle between the stable and the center direction, there should be some distance, angular distance. So if you take the angle, so this is my typical angle, between the stable direction and the center direction, it should be bigger than 1 over.
Minus n, which branch you choose, or you are on Lambda?
Well, it's diffeomorphism, so yeah, capital F is a diffeomorphism. Yeah, so capital F is a, okay, it's not there anymore, but capital F is a diffeomorphism of this. Yeah, it's just
Also invertible except just one place.
yeah.
Okay.
Yeah.
Reminds me a little bit what people do with Canona practice.
Well, that's actually exactly what we're discussing.
I try to show some kind of.
So I hope that reminds you.
Better.
Okay, it's eventually going to be. Okay, so all right, so we have the 3 definitions of regularity. Let me tell you what they do.
Elimination, stable.
Yeah. Okay. So the first thing I'll tell you about is number 1. Well, I mean, so number 1 and number 2, they give you a similar thing. So I'll tell you kind of in detail about number 1, and then number 2 will be something analogous, right? So if you have forward regularity, what does that give you? So let's say you have forward regularity for this point P. So we have point P. Actually, you know what? I need to draw a picture as well. So let me erase this. So and use this to draw a picture. Okay, so we have forward regularity. So we have P naught. And as we go forward, 1, P2, P3. Yeah. Etc. Then we have a stable direction, ES of P naught. And you can just transfer the stable direction to all of the forward orbit points just by taking its image, the derivative. 1. And if you measure the derivative, the growth rate of the derivative along the direction, then it should be bounded above by that quantity, right? So if you have that, then this is what you get. So you get actually 4 different nice consequences. Then, first of all, F is linearizable on, okay, so what I'll call forward epsilon shrinking 1 over L neighborhood of P. Okay, so if you're familiar with percent theory, you kind of should have an idea what that means, right?
It is in coordinates.
Yeah, that's right. But just going forward. So what I mean by forward epsilon shrinking 1 over L, P naught 1 over L. Right? And then as you go forward, you draw smaller and smaller balls. So each time you go forward, you shrink the size of this ball by lambda to the epsilon. So at P1, you'll have a slightly smaller ball, and the radius will be 1 over L lambda to the epsilon. And you draw an even smaller ball. This will be 1 over L lambda to the 2 epsilon. Right? So let me call these balls U0, U1, U2. Okay, so the radius of UN is going to be 1 over L lambda to the epsilon. So you have a shrinking ball, okay? And F is linearizable, meaning that on the restricted to these balls, you have this change of coordinates. I'll call it B0, B1. Ooh, for strategic reasons, let me draw this pointing this way a little bit. P1 or P0, P1, P2, and so on. So there'll be change of coordinates on these balls. So you get downstairs, you get these balls again, kind of shrinking. And what this change of coordinates will do, it'll take the point, the orbit point, it will map it to the center, so it'll go to 0. It will take the stable direction and it will map it to the vertical direction. So it'll just map it on the y-axis, like this. And when you take the dynamics of F and you restrict it, when you under this change of coordinates, the map just becomes linear. It just becomes 1, 0, 0, 1. So when you view the dynamics of F in these new coordinates, it's just going to be linear. Right? So this yes. Well, I mean, this immediately, as a consequence, you know that if you take the vertical axis and if you pull it back by the coordinates, then it's going to map to the stable map.
You need to assume C1 plus epsilon, but you assume it's C2.
Exactly. Okay, but I'm getting ahead of myself. So if you take these coordinates and if you factor F through these coordinates, then the F is just going to become a diagonal in your map. So downstairs, the axis of F is just neutral in the horizontal direction, but it's uniform contraction.
Yeah, okay, so if flat goes to 1,
yeah,
priori preserve this, then deal with that. But is there any way to keep this to centimeter?
So I thought in the error preserving case you have one positive, one negative. No? Oh, you have 2 center? Yeah, so that
Not double, I mean, in some ways you will along periodic orders.
right, yeah.
Hyperbolic periodic orders, but along the second.
Yeah, so that's the thing. So this the whole kind of story that I'm building, it really depends on the fact that you have strong domination along the stable versus the neutral. So I don't know what how it will work. It's very interesting. That's very interesting. And that's one of the challenges. So I told you that for the Henon family, which was kind of our initial kind of class of examples that we had in mind, this theory kind of works for up to Jacobian 1/4. And I think that's one of the biggest barriers to trying to go up to 1, is that as you go up, the domination starts to weaken and then the geometry is less controlled. So I don't it's the question after you kind of figure out this.
You were not
No, we didn't even know. Okay, but let's go back to this. So it's linearizable in this sense, and as Felix pointed out, the stable manifold on orbit point intersects the balls, this epsilon shrinking ball, I. This is going to be just equal to the pre-image of the y-axis. Okay, so that's clear enough, right? Because I mean, under iterating by this map, the only thing which contracts by lambda is going to be the vertical. And then C tells you that actually it's more than just what these curves identify as. If you restrict to these balls, then the geometry is bounded. The geometry of the stable manifold is bounded. So I'm going to phrase that as follows. If you take the stable manifold, the I, and you intersect it with this ball, then it has bounded term. So what does this mean, bounded turning? Well, if you have a curve in R2, right, then you would say that it has bounded turning if you were to look at the unit tangent vector and you look at the rate at which it spins, at which it turns. Right? And that should be uniformly bounded as long as you restrict yourself to this segment of the statement. So this epsilon should be, so if you have 4 regularity, then you have control of the geometry to the table. I'm trying to rate it very slow. And then one more is that the stable manifold, it depends continuously on the set of points with uniformly bounded regularity. So it depends, actually better than continuously, it depends C1 plus alpha continuously on T, which is forward L epsilon. Yeah, exactly. So let's say this is the tangent unit tangent vector to a curve, then well, let's say theta. So parameterize the vector. Let's say this is the argument. Let's say is parameterized by the arc length. Then bounded turning means that theta prime is bounded by some uniform.
And then at some point, the neighborhood will contain a critical point, and then we'll go forward.
So you're getting ahead of us.
That's the definition of the unimodal.
That's you're getting ahead of us.
Are you sure you want us to start? Here, the tangent vectors, so then we lose this one.
Yeah.
Maybe we can only see
No. So
you want to change because we discussed tangent vectors and curves. So.
right. So the tangent vector is C alpha.
Yeah.
So the curves themselves.
We integrate, but we integrate from one direction only. So I'm not so sure whether
yeah, but I guess it's kind of true, and it's technical, but C1 because I mean it's in another paper, so I'm not responsible for that. But then it's actually C1 plus alpha. In fact, for stable manifold, it's actually C2 for stable manifold, or maybe C2 minus alpha. Yeah, but for center, it's going to C1 plus alpha is the best. Okay. So this is what you get if you have 4 regularities. So you know information about the stable manifold. What if you have backward regularity? Instead of 1, if you have 2, then you have the analogous statement except for the backward regularity. Right. So if you have backward regularity at P0, then you can start to iterate backwards. P minus 1, P minus 2, P minus 3. Then again, we have epsilon shrinking neighborhood going backwards. This. And then we have linearization of F on these charts. -2, -3. Let's say this is -3, U -2, U -1, and so on. And that will give you balls like this. Ball downstairs. It will map the orbit point to the center to the origin. And if it's backward regular, you have the same center direction. The center directions will be mapped to the horizontal direction. And the map is again linearized to the diagonal. 1, 0, 0, lambda. 1, 0, 0, lambda.
This one, you convert contraction. Central is not enough. You need at least weak contraction.
Yeah. So if you assume backward regularity, then because the Jacobian is less than backward regularity. Yeah,
so you have maybe some expansion.
Yeah, but it's lambda raised to power epsilon, so it's very, very close to 1.
Nevertheless,
yeah.
When you go backward and in the central direction, you can have expansion.
Yeah, you can have very weak.
On your picture, it looks like going backward to contraction.
Going backward, you have contraction. No. So the center direction is placed on the horizontal. So going backward, you have.
It's like this. Along the center, you have weak contraction. So
Yeah.
that's why you can hold these small discs.
Yeah.
But maybe you have weak expansion backward. Then I don't understand.
I think Felix is asking about the second. You're looking at backward dynamics.
Yeah.
Always dissipative math, so this should kind of grow.
Oh, yeah. So these discs aren't defined dynamically. So it's not like I'm taking the disc and then I'm taking the image as I go backwards, because that will definitely make sense.
This we have very weak expansion.
Yeah.
But
All on the center.
you even cannot define uniquely this unstable manifold because it is central manifold, because it is defined like that. You go very far to the back. Yeah. And then you go forward.
Yeah.
Take limit. But if you go forward, if you don't have expansion, you get nothing with extension to the fourth plane. And then you get some result, but it is not unique.
Yeah.
There's no uniqueness of central mains. So
Actually, I failed to point this out. Central manifolds are not defined.
So that's why I object to this picture.
So I mean, you can define, like, you can just make some choice of central
Then you
manifold.
can get nothing, no stable at all. If you have weak expansion going backward, then you have no way to define stable unless you reach to something non-unique very far.
Right. Okay. So
when lambda is less than 1, then you have weak shrinking factor. And then it's okay. You have uniqueness and you have of time. It allows weak expansion, then
yes, that's right. So I agree with you 100% that the center manifold is not unique. Center manifold is not
you have troubles
with
you wrote some binarization.
Yeah. So actually, this is it can be worked out. So as long as you have this kind of bound, you can do a change of coordinates to make your map. In fact, you could just even choose this to be linear, the change of coordinates, and you will get your map to be C1 close to this diagonal linear map. And then you just define the center manifold as just the pullback of the horizontal axis on the disjoint. And it won't be a unique choice, but there is a caveat that the jet of the center manifold, even though the global center manifold is not unique, the jet will be. Well, actually, when we're discussing the backward regularity, we don't assume number. So we're only assuming. You just
Okay.
yeah, we're just assuming
We have central
Yeah.
direction, but we don't have central manifold.
no, neither key. Yeah, actually, it took us. The center manifold just take the horizontal axis. I keep saying the center manifold, but it's really a center manifold. It's not unique. So you'll get some locally invariant curve. And so this will be the pre-image of the x-axis with the center direction. And the bounded turning is true as well. Let's go backwards. If you have backward regularity. And you also have the 20 of the center as you go backwards. you have two, you have analogous.
So the negotiation you have on free.
Okay. Talk about it as well as forward and backward regularities. Then you don't have to consider backward orbit and forward orbit distinctly. You can actually glue them together. Have one consistent series of charts, and the transition from here to there will also be linear. So what that allows you to do is you take this center direction and you push it forward. And you take the stable direction and you push it backwards, or you pull it backwards. You take the like this, and then you raise it up, and then you get stable manifolds upstairs, and center. So you get this nice by infinite chart linearization. It's actually it's a technical one, but it's something that you can derive from assumption 1 and 2, which is what I'm calling gamma homogeneity. Secrets. Which there exists gamma, arbitrarily small. That's the following two conditions is going to be way smaller than epsilon that we get to satisfy. First of all, the Jacobian is almost constant. So the Jacobian F on P in lambda is but the for different points, the Jacobian will deviate away from lambda by at most exponent gamma. So it's going to be at most minus gamma, lambda plus b for different points. So you have almost constant Jacobian.
But this is 1, 2, and 3 angle is.
Oh, no. So this is before we get into quantity. So just our map.
Nevertheless, for one direction, some other numbers.
Right, but
if angle is
yeah, well, for a regular point, yeah. And the second assumption is that
you cannot shrink exponential anyhow because of 1 and 2. You cannot have angle shrinking exponential.
The strongest contraction that you can have is pretty much lambda, and the strongest expansion that you can have is pretty much. That's the thing.
Okay, go on because.
Oh yeah, it's okay. Yeah. So this is something that you can get from assumption 1 and 2. Not immediately, but you can replace F with a big renormalization, and then you'll have the points.
Oh, so this secret assumption is for some high renormalization.
High renormalization.
My concern is that you will draw here this blue arrow.
Yeah.
And blue arrow can shrink.
Yeah.
That's
So, but. Yeah.
Arrow this time. Yeah. It's parabolic. So here it's contraction. So. You have even something we stable contracts.
Yeah. shrinking faster than that. Yeah.
So this is Q.
That's
Fine.
Yeah. But if I write that down and it can come up, then it confuses people. I just kind of simplify. But yeah, it should be something.
What you mean now?
It's actually not epsilon squared. I think it's more like epsilon.
In central direction.
Yeah.
In central direction, you want shrinking?
Yeah.
Or
Shrinking as you go backwards and it should be shrinking much faster than the control.
Okay. When you go backward, if you have some weak shrinking, then this picture has to fall.
Yeah.
Okay.
Yeah.
Projections are clear.
Yeah.
Okay, then I'm not getting that thing about normalization.
Yeah.
The covenant of higher normalization is 0.
Well, it'll be close to it. So lambda will be very, very small. So because it's so small that when you raise it to some.
So it's not the same. It's not the same.
No, it's not the same lambda.
It's not the one. It's not the one that is.
Yeah, exactly. It's going to be lambda to the power, whatever.
Just parabolic.
Okay. At least define partially hyperbolic. If there exists L bigger or equal to 1 and epsilon equal to 0 such that every point in lambda is L uniform. Okay, and once you have uniform partial, it's nonsense of epsilon. So if you have some uniform partial probability, then you can just actually take bulk of 1 over L, and you have this in there. Right, so it's a much well-controlled system. Yeah. But the problem is that if you're assuming infinite renormalizability, you can't possibly have a uniform partial probability. For the same reason that if you have a diffeomorphism in 1D, it can't be infinitely normalized, more or less. Yeah. So something has to go wrong with the regular. And what destroys the universe, and then probably at the end. So let's say Cm, which is defined as the m iterates on C naught, and this is in the odometer. Let's call it is a regular critical orbit. Of quadratic type. If the following three conditions are set. Okay, so we have an orbit, it's a very special orbit. It will not be typical in the sense of measurable distance theory. So you have the following picture. You have C naught, C1, C naught, C1, C2, C3, and then you go backwards, C minus 1, C minus 2, and so on. Okay, so you have this orbit in the odometer. We say that it's a regular critical point, critical orbit of quadratic type if the following is true. So first of all, actually, maybe let me save this for bottom of this board for pictures and go there. First off, what is it? First off, the critical point, C naught. Well, actually, no, let's start with the critical value. C1, the critical value should be forward one epsilon rate. So I choose one, but it could be
One-dimensional, you're talking about diffeomorphism.
we'll talk about different. So I'm going to define what it means for it to be equivalent. Right? So this is definition.
Oh, but then we have to look at our points not and we define this.
That's okay. That's satisfied with properties. Yeah. So the first property is that C1 is forward regular. So it has the stable direction on which you have the exponential contraction. I landed to the end almost. And then you have the stable manifold as well. No, as long as it's somewhere. I just chose one because it's convenient. And then 2 is the critical point. So this point should be backward. 1 epsilon. So you have the center direction. And the center manifolds. This. And of course, if it's forward regular, then you have these epsilon string involved, which can be linearized. And same with backward. Which puts the center manifold horizontally, and it puts the stable manifold vertically. And the point is like and so on. Right? Okay, so here's a crucial third assumption. So if you're looking at the center direction at C1, and if there's some angle between the stable and the center direction, then this will just be a piston regular point. It'll just be a typical point, right? So we don't assume that. Well, we assume the opposite of that, that they're actually coincide, the center and the stable direction, right? If the center direction, well, the center direction at C1 is just the image of the center direction at C0, and if they coincide, then the center manifold and the stable manifold should have a tendency, right? So we say that it's quadratic type if the tendency is a quadratic type. 3, if you take the center manifold at C0 and you map it, then it has, so if you map this center manifold, it will look like this. Okay. So this is what it means to have a critical point in this diffeomorphism setting. And let's see what that looks like downstairs. Well, if you look downstairs, the transition from the critical point to the critical value cannot possibly be linear, because that would just make the horizontal go to the horizontal, where the horizontal has to map to a side of the front. Right, so the transition actually shouldn't be a linear map, but it should be, well, I mean, you can pick different candidates, but I think the best candidate would be to choose a Hanel map. So it's x squared minus lambda y. So
Here can we assume forward and backward
yeah, so we assume 1 and 2, and then now we assume. So we assume that C1 is forward regular, C0 is backward regular, and then to glue them together, you can't glue them together in the way of Cassin. You have to glue them together in this critical way, in this atypical way. Yeah.
So I mean, so the based on the condition 3, the blade now is
yeah, that's right. With this new condition. And well, I think it's nice to kind of draw the analog from 1D. In 1D, if you have the critical orbits, at the critical moment, it's modeled by power x squared. But away from the critical, it's just diffeomorphism on the critical moment. Same way here. At the critical moment, it's modeled by, well, the analog to the analog of power map, which is the Hanel map, and then backward and forward is just linear. Okay. And you notice something else, and this is something that Dennis pointed out, is that when you go through the critical point, the geometry is messed up, right? And this, you can easily see that this gives you unbounded geometry of the stable and center manifold, because if you iterate this forward, then well, there's contraction, right? So the turning is going to slow. This kind of parabola. And same thing, if you pull this stable manifold backward, it will be a parabola like this. And if you start to pull back, there'll be the stretching vertically, and so you have this sharp corner. And so any system which has a critical orbit like this cannot be uniformly partially hyperbolic, but we say that it is unimodal if that is the only source of non-uniform partial hyperbolicity. So definition. F is unimodal if outside these balls, where we have linearization, where we have uniformization of the critical orbit, you have some uniform hyperbolics. Outside VI's, P is L delta regular, sin regular, for some uniform L and this is what it means for diffeomorphisms to unimodal. And of course, a definition is all well and good, but it's kind of meaningless if there's nothing that satisfies this definition. Let me just say that there are some. Okay, so here's the most unsatisfying part of this project is that condition is very hard to verify. Unimodality is very hard to verify, but there are examples where we have it. And well, it's mainly kind of the Helmholtz family. So you have the map xy, and it maps to x squared plus c, or let's try to by a and b to emphasize that this is real. A minus b y. So this is the Helmholtz family. And okay, this is the parameter space A, B. Yeah. Okay, so here's what we have so far is that if you have a one-dimensional renormalizable map, so the one-dimensional maps are when the Jacobian is equal, then you just have x squared plus a, and you can just ignore the technical. Right, and then you just have one-dimensional quadratic map. If that's infinitely renormalizable, then well, this will be proved it. And then if you were to perturb it into 2D, if you were to increase D a little bit, then as long as you have bounded combinatorics for 1D, then you know that when you perturb it a little bit, you are unimodal. And so it's not this set of unimodal. Small perturbations of infinitely renormalizable 1D maps with bounded combinatorics is still unimodal. I suspect that it's true for unbounded combinatorics as well, but it's not true. And here's just one more thing I'll state before finishing is that, let's say we take the five. Let's say this is F C. So this is the 5 non-quadratic polynomial, right? And we know by the work of Lyubich, Martins, and Dissipative that there's for some small Jacobians, there's some real analytic curve which are infinitely renormalizable, unimodal, and when you renormalize it, it converges to the 5 renormalization. Right? But probably this curve goes beyond S. Right? And computations show that it actually goes all the way up to the Jacobian. Right? So we don't actually know this. We only know that it goes up to epsilon. We don't know how much further it goes. But as far as it does go, all of those maps are going to be. So as long as a map is infinitely normalizable, and when you renormalize it, it converges to some 1D unimodal limits, you know that the map is unique. But right now we don't know. And I'll just say verbally the main theorem. The main theorem will allow us to prove that if you're looking at this family, for example, and you know that the map is unimodal, then you will know that it actually belongs on this curve, which goes to one dimension. That's what the main theorem is. But the problem is, if you just give me a map, now we don't know how. Okay, I should stop here. I probably went over something.
Read again this definition of unimodal.
New eyes are default.
You want to say that one freeholds and outside of the other.
Yeah. 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 Then it's unimodal. It's true. We have a freehold, which let you control that zone.
Questions? Yeah, coffee or lunch, maybe.
Well, maybe chat has a question.
Maybe somebody online. Who is Caroline and Michael still?
Any questions in the chat? Because I think the live audience is in this chat as well.
Generalize it.
So how would I? So then like if you return 1D Fibonacci, what you get? Is there any work on it? Okay, so somehow Fibonacci is easier than
I don't know.
Eigenbound?
Yeah,
I don't know. That's
I think that there is no Fibonacci to events.
Oh, yeah, actually he also
Problems like Marco also, Vivian also.
yeah, that's all right, that's very interesting. Actually, I also heard that.
No.
Yeah, I don't.
What is the statement? The popularity.
Is that okay? Okay, 1 minute. So in 1D, what is the statement of perfect bounds? Well, there's different statements for perfect bounds. In 1D, here's one version. You start with the critical point. So you have some level n, normalization level n. You take the normalization p containing the critical value. You iterate by f. Let's say point right to the n minus 1. That takes the p containing the critical point, right? And one version of a perfect bound is that this map is uniform bounded. Okay? In 2D, we define the critical value. Yeah, critical point, right? And what we say is we have a renormalization domain of level n as the critical point and the critical value like this. And the upper bound says that there is some vertical and horizontal foliation, which can be straightened into genuine vertical and horizontal foliation by some C2 map with uniform distortion, such that if you factor the return map f2 to the n minus 1, if you factor the return map through this foliate, then it becomes a diagonal map. So xy just goes to I don't know, hx vy. and this had a boundary. So the way it maps the vertical lines is
Functional speed. Yeah, I mean, you can say a priori balance is preservation of a subset of bond that is working by under normalization or spreading code.
Oh, okay. I don't know. I mean, this kind of for me was direct generalization of the kind of control that you had for that Lyubich Martins and the Cabal developments.
Okay, and you also mentioned that you said that the family you said that you know that unimodal. You said something about convergence to the one dimensional.
Yeah. So if okay. So right. So okay. Well, I mean, I guess it's kind of vague, but so the theory of the assumption is that if you take the 1D renormalization fixed one, let's say 5, and then you look at the stable manifold and the renormalization operator, there should be a way to extend that to 2D. And so far it's only been extended up to epsilon, but for as long as we can extend it, so there should be some non-linear the coordinates
Any kind of so under your assumptions, you model mass and so on and so forth with a priori bond. Do you have any kind of hyperbolic courses?
Hyperbolic courses? Oh, for the renormalization operator? I would feel like isn't that already done, right?
Well, for no.
Oh, for this. I guess we didn't get it.
That seems like
but the thing is, I don't know if like it forms a nice complex set of unimodal maps. Probably you can make a nice function set. Unimodal diffeomorphisms.
More questions?
So let me this Riemann 1/4 theorem. How does that enter? There is this quarter appearing, right? Can you remind me about that? I heard that before, but
so I mean, if we use it at the very beginning and then we forget about it, which is fortunate because I don't actually kind of know. I only know the statement of the Riemann theorem. I don't know how it's proved.
I mean, it's essentially about subharmonic functions actually in the plane.
Right. So the only way we use it is that we know. Well, I guess for this you don't need to use it because yeah, actually no. For the content of this talk, you don't actually use that at all. The only way that I guess it would enter into the discussion later is that if it's less than 1/4, that the maps are properly dissipative. So if it's less than 1/4 for the heteroline family, then you know that it's properly dissipative, and you know that at the boundary of zero entropy, the maps are normalized. So then you have this class of maps that satisfy the two assumptions that we needed to kind of get this discussion flowing. We still don't, not yet. For the Hamilton, what? That is unimodal?
Yeah.
No. We don't know up to 1/4. We don't know.
But up to 1/4.
Yeah. Up to 1/4. We don't know. Okay. But yeah, that's what we're. Does that answer the question? The silence. Silence. Probably will wrap. Okay.
Thank you.
Thank you.
For this